Hello everyone, I hope you are all fine and doing well. As of now, I made 29 lectures on this YouTube platform, and in that 29 lectures we had gone through the concept overview and problem solving in ionic equilibrium chapter. Today I am here with a new chapter, that is chemical equilibrium. Chemical equilibrium. Chemical equilibrium. Before we are going to learn about chemical equilibrium, we should know one thing, that based on the extent of completion of reactions, reactions are classified into two types. I repeat, based on the completion of reaction, reactions are classified into two types. Those are irreversible reactions and the second one is reversible reactions. Right? So, irreversible reactions. Irreversible reactions are the reactions in which reactants are completely converted into products. I repeat, irreversible reactions are the reactions in which reactants are completely converted into products. That is, in the reversible reactions, if we take the reaction R gives rise to P, that is R represents the reactants and P represents the products. Reactants are completely converted into products, that is 100% reaction takes place. And moreover, irreversible reactions proceeds in single direction, right? Proceeds in single direction, right? So, irreversible reactions are the reactions in which reactants are completely converted into products and the 100% reaction takes place. Examples for reversible reactions are all combustion reactions, that is 2mg plus O2 gives rise to 2mgO, CH4 methane plus 2O2 gives rise to CO2 plus 2H2O, and most of the decomposition reactions, that is 2 KClO3 gives rise to 2 KCl plus 3 O2, and all precipitation reactions, that is precipitation reactions. Precipitation reactions, that is barium chloride plus H2SO4 gives rise to barium sulfate plus 2HCl. So, these are the examples for irreversible reactions. In these reactions, reactants are completely converted into products, and in such case we can call it as 100% reaction takes place, right. And decomposition reactions, 2KClO3 gives rise to 2KCl plus 3O2, that is also a irreversible reaction. Precipitation reactions, those are also examples for irreversible reactions. Now, let us learn about reversible reactions. Reversible reactions are the reactions in which reactants are not completely converted into products. I repeat, reversible reactions are the reactions in which reactants are not completely converted into products. And moreover, reversible reactions proceeds in two directions, that is reversible reactions. If you take an example of example reaction, that is reactants gives rise to products, because in this reversible reactions reactants are not completely converted into products, that is reaction 100% reaction does not takes place. So, reactants converted into products and products converted into reactants, that is 100% reaction does not takes place, because in which reactants are converted into products, but this reaction does not complete. Okay, and after the formation of products and without completion of this reaction, products undergoes chemical change, that is products start to form reactants, that is either reactant to products reaction is not complete, and products to reactants reaction is not complete. So, reversible reactions are the reactions in which reactants are not completely converted into products, and moreover reversible reactions proceeds in two directions, that is reactants to products and products to reactants, that is from left to right and right to left. But whereas in the irreversible reactions, reactions proceeds only from left to right, that is reactants to products. But whereas in the case of reversible reactions, reactants converted into, that is reactants converted into products and products converted into reactants. So, reaction takes place from left to right and right to left, and in this reversible reactions actually in fact in this reversible reactions tug of war has been takes place due to that tug of war takes place between reactants and products, there establishes a equilibrium, as like in the tug of war game, right. So, there exists a equilibrium, right. So, equilibrium established only in reversible reactions, only. And one more important point that should be keep in your mind, that reversible reactions equilibrium established in reversible reactions, and reversible reactions that is in reversible reactions equilibrium, formation of equilibrium takes place and that reversible reaction should be carried out in a closed vessel. That is, if that is reversible reactions equilibrium established in reversible reactions only that reversible reaction is carried out in a closed vessel. This point is very much important because equilibrium established reversible reactions, but if you want to establish a equilibrium, that reaction should be carried out in a closed vessel. That is very important point, right? So, and examples for reversible reactions are H2 plus I2, H2 gas plus I2 gas gives rise to, that is double headed arrow, that incompletion of reactions are represented by double headed arrow, 2HI, right, and N2 plus O2 gives rise to N2 gas, O2 gas gives rise to 2NO gas, and 2SO2 plus O2 gives rise to 2SO2 gas, O2 gas gives rise to 2SO3 gas, and N2 gas plus 3H2 gas gives rise to 2NH3. This is also a gas. And one most important example is calcium carbonate, CaCO3 solid, which undergoes reversible reaction and it forms CaO, calcium oxide solid, and CO2 gas, and NH4HS, that is solid, NH3 gas plus H2S, H2S gas. Okay. So, these are the examples for reversible reactions in which equilibrium is established, because in reversible reactions tug of war has been takes place between forward reaction, that is, and backward reaction. Reactants gives rise to products. This is a forward reaction, that is left to right, and products to reactants, that is it is a backward reaction. Already I told you reversible reactions proceeds in two directions, that is forward direction and backward direction. At the when the equilibrium established forward, that is I shall discuss the rate and whatever the remaining concepts in the next video. So, reactants to products is a forward reaction and products to reactants is a backward reaction, and these are the examples of reversible reactions. Okay, H2 gas plus I2 gas gives rise to 2HI. Okay, and if you observe these examples with your naked eye, if you observe these examples with your naked eye, you can observe one important point. The chemical pieces, the chemical species which are undergoing in reversible reaction forms a new chemical species, that is H2 reacts with I2 to form another chemical substance, that is 2HI, that is a new chemical species, and N2 reacts with O2 that forms 2NO gas. This is a new chemical species, and these chemical reactions, whenever these chemical substances or chemical species are react together, they form a new chemical species, that is what we call it as chemical process. So, in reversible reactions, chemical process takes place. Of course, in irreversible reactions also chemical reaction chemical process takes place. And if you know that H2 gas, I2 gas gives rise to 2HA, that is a chemical process, and this chemical process is a homogeneous chemical process, that is a homogeneous equilibrium. We can call it as a homogeneous equilibrium. The equilibrium established in this reaction is called as a homogeneous equilibrium. And when we go with this example, that is calcium carbonate solid gives rise to CaO solid plus CO2 gas. So, if you observe this reaction, calcium carbonate undergoes reversible reaction, and calcium carbonate is a solid and it forms calcium oxide, it is a solid, and CO2 it is a gas, and in this reaction also chemical equilibrium is established, and in this reversible reaction solid gas. So, this solid material or this solid chemical substance undergoes a physical process, because upon decomposition of calcium carbonate it forms a solid and gas also. So, physical process, it forms a different physical state species, that is solid and gas. So, in reversible reactions physical process also takes place. So, in reversible reactions chemical process and physical processes are takes place, right. So, chemical process and physical process takes place in reversible reactions. Okay. Of course, we should note this point in case of reversible reactions only, because in the latter concepts we should represent that physical change with different representation, with different letters or different representation, right. So, and therefore, what we understand from this types of reactions is that, so based on the extent of completion of reactions are classified into two types, that is irreversible reactions and reversible reactions. But in reversible reactions equilibrium is established, okay, and that equilibrium and the establishment of equilibrium which undergoes in that which includes chemical process and physical process, and moreover equilibrium is established in reversible reactions. And one most important point that you should remember in your mind is that in reversible reactions we can apply law of mass action. For reversible reactions we can apply law of mass action. What is that law of mass action? So, in this chemical equilibrium chapter we always confine to reversible reactions, right, not irreversible reactions. So, for reversible reactions we can apply law of mass action. Law of mass action. What is law of mass action? Law of mass action is nothing, is that the rate of a chemical reaction is directly proportional to the product of active masses of reactants. I repeat, the rate of a chemical reaction is directly proportional to product of active masses of reactants. right? Active masses is also called as active masses. Active mass is also called as activity. Active mass is also called as activity. And one more important point is that activity is equal to, for solutions, activity is equal to molar concentration into activity coefficient. Molar concentration into activity coefficient. And for gases, activity is equal to partial pressure into activity coefficient. So, and one more important point is for dilute solutions and gases, activity is equal to 1. That is, activity that is represented by A is equal to molar concentration, that is represented by C into gamma. So, in case of solutions, concentration is taken molar concentration, we consider the molar concentration, but in case of gases, we consider the partial pressure. And for dilute solutions and gases, activity is equal to 1, because for dilute solutions actual concentration is equal to activity coefficient, because activity coefficient is equal to 1. Why that activity coefficient is equal to 1 also I was explained in the pH concept. Okay, you please refer that pH concept lectures, so that you came to know why that gamma is activity coefficient is equal to 1 for dilute solutions. If activity coefficient is equal to 1, then A is equal to C, activity is equal to actual concentration. And for dilute solutions and gases, activity is coefficient is equal to 1 and activity is also it also equal to 1, right? So, for what you should remember throughout this chapter is equilibrium established only in reversible reactions, and equilibrium established in reversible reactions only if that reaction is carried out in a closed vessel. So, if you want to establish a equilibrium in a reversible reaction, you should carry out that reaction in a closed vessel. And in that reversible reaction, two processes takes place, that is physical process and chemical processes takes place. And one more thing is that for reversible reactions we can apply law of mass action. What is that law of mass action? The rate at which this reaction takes place is directly proportional to the product of active masses of reactants, and activity is equal to molar concentration into activity coefficient for solutions, and for gases activity is equal to partial pressure into activity coefficient. These points should be remember in your, you should remember these points in your mind. Entire chemical equilibrium concept, chemical equilibrium chapter. Okay. So, in the next video I shall come up with we shall discuss, we shall learn characteristics of equilibrium, equilibrium constant, and expression of equilibrium constant. Okay, thank you for watching.